first properties of L'Hopital's rule is limit x tends to a, fx is equal to 0, and limit x tends to a, g of x is equal to 0, or limit x tends to a, f of x is equal to plus minus infinity, and g of x is equal to plus minus infinity. We want to see where we can use the L'Hopital's rule and where we can't. So first, let me show you the type of limits which can be converted with the help of L'Hopital's rule, and these are the methods or conditions, or you can say the properties which we can use that to know like if this question is going to be converted with the help of L'Hopital's rule or not. So the limit would be look like this: limit x tends to a, f of x upon g of x. If limit x tends to a, then fx upon gx would be in the form of 0 by 0. Then we use that the first one, this one we can use here. Yes, and let me change the color so that would be easy to visualize. Okay, and where we can use this fx is equal to plus minus infinity. So if the type of limits like infinity by infinity form, minus infinity by infinity form, and infinity upon minus infinity, and minus infinity upon minus infinity, if this type of limits we get, then we can use definitely the L'Hopital's rule, and this is the properties. With the help of that we can got to understand that this is the limits, and if it is the form of 0 by 0 and infinity upon infinity, minus infinity by infinity, infinity upon minus infinity, and minus infinity upon minus infinity, so we can use that. And another property, let me show you the second property for the L'Hopital's rule: g dash x is not equal to 0, f dash x and g dash x exist. We need to remember that this property, the first property verified, then we go for the second property and we check the second property, like it is verifying the second property of L'Hopital's rule or not. And if it is not verifying the all the rules or properties of L'Hopital's rule, so we can say that this question or this limit is not solved with the help of L'Hopital's rule. And third property is going to be, let me change the color. Yes, third property is limit x tends to a, f dash x upon g dash x. If it is exist, then what we can say, limit x tends to a, fx upon gx is equal to limit x tends to a, f dash x is upon g dash x. So this is the three properties which we can check for the L'Hopital's rule. And in third property, what we have, the limit x tends to a, f dash x upon g dash x. If it is exist, if it exists, then we can say that limit x tends to a, fx upon gx is equal to limit x tends to a, f dash x. It means that the differentiation of the denominator and differentiation of the numerator both will exist, and we can do that for. And we have seen the relationship between the differentiation and limit interchangeably, we have seen in the previous lecture. So this is the third property for the L'Hopital's rule. Okay, let me show you the some examples that would be easy to understand the L'Hopital's rule. Example A: limit x tends to 0, sine x upon x. So we know that first we will check the first property of L'Hopital's rule. So if limit x tends to 0, so we can put the x is equal to 0 at the place of x. Then sine 0 is going to be 0, and in denominator we have only x, and x is tending to 0. So this is the 0 by 0 form, what we can say here. So this is first property of L'Hopital's rule is verified. Now we go for the second property, and in second property we know that the gx is not equal to 0. Then first we will differentiate the numerator and denominator. So if we differentiate the numerator, then limit x tends to 0, this is going to be cos x upon 1. Yes, sin x differentiation is cos x, and x differentiation is 1. Yes, so this is going to be, if we put x is equal to 0 at the place of x, then cos 0 is going to 1, and 1 upon 1 it becomes 1. Okay, let me take another example. Example B: limit x tends to 0, square root of x plus 9 minus 3 divided by x, which is equal to limit x tends to 0. Then if we differentiate the square root of x plus 1, then this is going to be square root of x plus 1 in the, this goes in the denominator. Let me show you what it would be. The 1 upon 2, this is the differentiation of the square root of x plus 1. And if we differentiate the constant term, then this is going to be 0 in the numerator, and in denominator we have x. So x, if we differentiate, this is going to be 1. It becomes 1. So which is equal to 1 upon 2 square root of x plus 9. And if we take the limit x tends to 0, and if we put x is equal to 0, then inside the square root we have only 9. And if we break that for the pair, then 3 into 3, and the 3 will comes out, and 1 upon 2 into 3, then this is going to be 1 by 6. Okay, let me take one more example, so that would be easy. You will be comfortable with the L'Hopital's rule. Let me take another example. What we can say, that C part. Limit x tends to 0, e power x minus 1 upon x square plus x, which is equal to limit x tends to 0. First we will check the first condition of the L'Hopital's rule. First we will check the first condition. So x tends to 0, and if x tends to 0, we put x is equal to here 0. Then e power x is 0. Then the value would be 1. So 1 minus 1 is 0 in the numerator. And if we talk about the denominator, there is only x terms, and x is tending to 0. So x square term is going to 0, and plus x is also going to 0, and 0 plus 0 is 0. Yes, so we have here is 0 by 0 form. And if we differentiate, now we are going to check the second condition, and then we check the third condition. First, let me go for the second property of L'Hopital's rule. Then e power x is different. If we differentiate, then e power x is going to be e power x, and the differentiation of a constant term is 0. So e power x upon 2x, x square differentiation is 2x, and differentiate x, then this becomes 1, which is equal to, if we take the limit x tends to 0, then we put x is equal to 0. Then 2 into 0 is 0, and in numerator there is a x term, and if we put x is equal to 0, then the value would be 1 in the numerator, and in denominator we have 1. So 1 by 1 is equal to 1. So this is going to be answer.